Cool. So today we are going to talk about Chardonnay fast and general data center transactions for on-disk databases. This was presented at OSDI 2023, and we'll be discussing this paper. So before starting, let's start with some background. The paper talks about strict serializability. It's also known as external consistency. It fundamentally boils down to supporting two things. First one is serializability. Serializability is some serial ordering of committed transactions, and linearizability. So suppose if you have a transaction A that commits before transaction B starts, A should precede B in the serial order. It also talks about two-phase commit. Fundamentally, two-phase commit boils down to two phases of committing a transaction. One is prepare, where prepare is kind of communicated to all the stakeholders, and a promise is got from all the stakeholders whether the commit can happen or not. It's and once the result is from all the stakeholders yes, then commit, all the participants have agreed, then the commit can go ahead in the second phase and we go ahead and commit the transactions. So what are the general problems that people talks about two-phase commit is, one is blocking. There is a coordinator that is required to run this protocol, and if a failure of this coordinator happens, it can prevent making progress. One solution is to have a replicated coordinator to uh, increase the availability of this coordinator and tackle this problem. So it also goes forward and talks about two-phase commits penalty. So the issue with two-phase commit is it requires two network round trips and two synchronous log writes to persistent storage, and this is per transaction. And coordination is necessary to guarantee isolation, which also kinds of decreases the concurrency. It also increases contention, particularly this increased contention is considered harmful for short-lived transactions, which are very common in OLTP kind of workloads. So their observation in this paper was, if they run two-phase commit, the latency of commit using this protocol in a single data center could easily crop up to double-digit milliseconds. So what is the requirement that they had? So they had fundamentally two requirements. One is making things fast, and the other is making things general. What do they mean by fast? When so general transactions for on-disk databases have to be fast. In terms of numbers, latencies for short OLTP transactions should be around 100 microseconds, whether it's happening in a single or a cross partition basis. Performance penalties of distributed transactions should also be relatively smaller. Another point that they have focused on is about supporting long running read only queries efficiently without impact on read write OLTP transactions. And they also focused on high throughput for both low and high contention workloads. And in terms of general, what they mean is that they want to support an unrestricted programming model, which is capable of supporting full SQL, highest level of semantics in terms of consistency, that is strict serializability, without overall scalability limits or use of any specialized hardware. So the general architecture is quite similar to shared nothing uh, systems that are already there in existence, with one change over here, that is an introduction of epoch service. So client is also acting as a coordinator of the two-phase commit protocol. It starts a transaction, registers this transaction in this TX state store, executes the transaction's read writes, sends a prepare to the KV service. KV service is where the database actually lies, and it gets the response prepared. But while doing that, this is 3A, it also parallelly sends read epoch, and it gets a epoch number which it makes use to make sure whether it has to proceed for the commit or not, or abort. So this is the general block level overview of how the architecture is laid out. Now getting into details of this. What is an epoch service? So it maintains a single monotonically increasing counter that is called as an epoch. Only one RPC read epoch is exposed to the client, which just returns the latest epoch. Reading epoch serves as a global serialization point for all committing transactions. Epoch is used to assign transaction timestamps at commit time. That's why in this figure, if we go back, once it gets the epoch to commit or not, it sees whether the number that it got, epoch number, is within the bounds of the epoch intervals that it is getting while from the result of the prepared phase. So epoch is only read, not incremented by each transaction. Getting more into details about this. So epoch service is multi-Paxos based replicated state machine. Leader increments, we all know that Paxos is leader based consensus protocol. So leader increments epoch at a fixed configurable time. For them, they say that the value is 10 millisecond by appending entry to the Paxos, and that's how it's replicated to. They say that they want to maintain monotonic epoch invariant. What is this invariant? So if a read epoch returns E, then all subsequent read epoch calls must at least return a value greater than or equal to E. And which in other sense means that it should not return a value less than what has been already read. Then what it says is that it also goes and further says and talks about this, that it cannot simply rely on reading the value from the leader replica, because what it is stating is that since leader might lose its status without realizing it for a while. This point I need to understand more deeply, and probably we can talk about it when such scenario kind of happens. But yeah, so what it then says is that, so what is the value that it should use for the epoch is then derived by asking all the replicas and considering the current epoch value that is returned by majority of the replicas. If a value has no majority, then client has to retry the reads. So instead of depending on the leader, it gets the values from the majority. That's what it is. Why? Is because they are stating that leader might lose its status. So then the next part, as we discussed, we saw here is the key service. So these are actually the 4 parts of the system: client, transaction store, state store, KV service, and epoch service. We talked about epoch service in general. We'll talk about the key service. So key service is the key universe that is partitioned into disjoint continuous subsets. We can call it as a range. Each range is assigned to a number of range servers, and each range comprises of database and also a val write-ahead log that is implemented via Paxos. They say that val has to be on a fast NVMe device for low latency, and they emulated this on top of DRAM. Database would be on commodity SSD storage, which kind of is not very clear that what do they mean by commodity SSD over here. One of the range replicas is leader and holds the leader lease. The leader also, because it's the leader, it also holds the lock table that is required to implement two-phase locking. And this lock is generally a range lock. You don't lock the complete table, you just lock the range for which the operation or update is happening. All read and writes obviously has to go through the leader. Let's talk about the transaction state store. Transaction state store is a store which is the truth source of a transaction. It stores the state of all the active transactions. It is fault tolerant, replicated, and they say that it's used also as an optimization to two-phase blocking. which they have mentioned in the appendix. Will not be talking that about will not be talking about it. Yeah. So this state has every transaction has simple like normal states: started, committed, aborted, or done. Service is hash partitioned by transaction ID. Each partition generally is assigned to 3 servers. Within a partition, each transaction state is multi-paxos replicated. There are 3 entries per transaction. Zeroth entry mentions that the transaction is started. Entry 1 says either the transaction is committed or aborted. And second entry says whether the transaction is done or not. This transaction state store is the actual source of truth regarding transactions outcome. Let's talk about client. Client is the interface for users to access the database. It also acts as a 2PC coordinator. When a transaction finishes execution, client reads. So I've not understood this part also very clearly. What do they mean by finish? Because after transaction finishes execution, they say that they do the prepare, which is kind of a misleading in one sense. So do they mean by a dry run over here, or what kind of finished state they are talking about was not very clear when I was reading the paper. But I would say that some kind of initiation of this transaction is happening over here. Then the client reads the epoch parallelly that we already saw from the epoch service to issue prepare RPCs to all the participant range leaders. Each leader corresponds with the prepared message, including the epoch interval on its lease. Client cross-checks its read epoch with the leases epoch interval of every participant. And if it is within the range, it can go ahead and commit the transaction durably in the transaction state store. If not, then the client issues the abort of the transaction. Client notifies participant range readers about the commit so that they can also locally record and release all the locks because they have held the locks for this transaction. Then transaction waits until commit to release the locks, which are needed for snapshot correctness, as is what the read is based on. So let's talk about snapshots. So snapshot reads are needed for efficient read-only queries. So queries need to be declared read-only from the start. If they are not declared read-only, they would be considered as read-write and will go through the normal path of execution. They talked about versioning. A basic idea of versioning is that every key is kind of tagged with a version ID, where version ID is a prefix of an epoch plus some counter which starts from 1, and this is needed to differentiate between different transactions in the same epoch interval. That's why this counter is needed. Then the read algorithm is like it follows this epoch ordering property. If epoch transaction 1 happened in epoch E1 and transaction 2 happened in epoch E2, and if E1 is less than E2, then transaction T1 precedes transaction T2. So all these epoch boundaries are consistency points for them. Because of this ordering, it ensures serializable snapshot reads. So the challenge that paper mentioned was ensuring snapshot is consistent. Which, what does it mean? It means that no transactions would commit with an epoch less than the EC. EC is the committed epoch that was taken into consideration. So it should not happen that a transaction, there are transactions which were happened at the checkpoint or the snapshot when it was taken and are yet to be committing. So till that point, every transaction should be committed. And they say that they go on and mention that in the appendix they have given a proof sketch of this. Will not be going over that, but the general idea is because of ordering of epoch and uh, of the and giving leases of locks and making sure that writes have locks in their paths, while reads, if they conflict with write, they'll just reads are lock free, but if they conflict with write, they will wait for writes to relinquish the lock, and writes will relinquish the lock when the transaction is committed, and then they'll be able to read, which means that that serialization point will be achieved. It also talks about prefetching. What they say is that with this fast two-phase commit protocol that they are basing on fast networking, instead of using gRPC, they make use of ERPC, which has latencies of microseconds, uh, and also fast store. So they say that the bottleneck actually moved to slow storage, which becomes a contention point. So then how to fix this? So they go on to say that a lot of prefetching has been done either by identifying read set and passing this read set to fetch the records in memory on the storage server. But then they say that for uh, dependent queries, identifying read set was difficult. So then they came up with a generalized concept of prefetching, and it's like execute the same query twice. First time that query will run in a dry mode. So every query that runs in a dry mode, uh, it will load all the read set that is required to the memory. And then when you execute it normally using two-phase locking, it will this storage bottleneck point will be resolved because whatever is needed for a transaction to commit will already be in memory. So the advantage is application logic. They also went ahead and said that there is one also advantage of this. If application logic decides to abort, we don't have to perform the actual execution. But there are a couple of disadvantages also that they mentioned, that obviously it adds to query latency because now we have added a dry run step prior to doing the actual run. And the second point is that execution of this whole transaction logic is happening two times before committing. One is while actual committing and one is for the dry run. So yeah, that was all from my side. Thank you. Questions, discussions?